Alright, so we're going to be looking at this situation here where we have a metal rod of a certain charge, a uniform charge too, and we want to find the electric field a certain distance away from it. But to do that, the best way to do that in this situation is to break up this whole rod into small little parts, little point charges essentially, and well, little parts and treat them as point charges. So that if we do that and apply it to the formula for electric field of a point charge, we'll get 1 over 4 pi epsilon naught dq, because that's the smaller charges, over r squared cosine of theta. The cosine of theta takes into account the angle that the little cross-sectional area is from our location that we want to find the electric field at. So we're going to want to take the integral of that because we want to add up all those little point charges. But we can't really do that while it's in this form. So what we're going to have to do is solve for dq. So we can say that dq over q, that would be that small charge over the charge for the whole thing, is equal to dy over L, because L is the length of the entire rod and dy would be the length of that small piece. So if we solve for that, we get that dq equals dy times q over L. And we're going to need to solve for r in terms of x and y as well. So if we use the Pythagorean theorem here, see we got a nice right triangle here. We get that r squared equals y squared plus x squared, and if we solve for r, we get that r equals the square root of y squared plus x squared, and that'll help us because we need to know the cosine of theta. And if we go back to that right triangle, we can see that the cosine of theta equals x over r. So r is equal to y squared, the square root of y squared plus x squared. So we plug that in, and we get that the cosine of theta is x over the square root of x squared plus y squared. So now that we've solved for that, we can plug those values into our original equation. So we definitely want to do a definite integral. We can say that we're going from negative half the length to positive half the length. And then we have our 1 over 4 pi epsilon naught. That's a constant, so we're going to bring that out. And then we plug in our dy times q over L for our dq, and we plug in our other terms there. We solve for r to be the square root of y squared plus x squared, and since it's squared, we won't have a square root. So the cosine of theta is x over the square root of x squared plus y squared. So we can pull out all our constants then. Q over L, that doesn't change. Now if it wasn't a uniformly charged rod, then we couldn't pull out the Q, and that would make things more difficult integration wise. And we can pull out the 1 over 4 pi epsilon naught because that's a constant as well. So then we have this integral here, this definite integral, and if we solve it, we get that 1 over 4 pi epsilon naught times q over x times the square root of x squared plus L squared over 2 equals the electric field at the point that we're looking for. So in that problem, we had that there was a charge of 6 coulombs, and that the rod was 10 centimeters, and the point we wanted to see what the electric field was at was also 10 centimeters away. So we plug those values into this equation that we've derived. We get that the electric field at this location, 10 centimeters away, is 8.16 times 10 to the negative 10 volts per meters.